His name is Chevalier de Mere. He asked Pascal. So Pascal is the person who created Pascal's triangle, which gives the binomial coefficient. If you have learned about Pascal, so you might be knowing about Pascal's triangle, which is very popular, which gives the coefficient of the binomial coefficient, a plus b square, a plus b cube, all these things. He asked Pascal for an explanation of his unexpected losses in gambling. So regularly he was losing a lot of money in gambling. He wanted to have an explanation from his mathematician friend Pascal. The famous correspondence between Pascal and Fermat. Fermat is the person for Fermat's little theorem, Fermat's last theorem, and all this analysis works, of course, was instigated back in 1654, and they were mainly interested to calculate the binomial sum. So that time, people Bernoulli, so Bernoullian family. So Bernoulli means in the literature you will be finding more than 15 Bernoullis. All of them belong to the same family, and all of them contributed to mathematics and statistics. So Bernoullian distribution was invented that time. Binomial distribution came as well as with the hand of Pascal, and some people say it's by Newton and many other things out there. They were discussing about something called how to calculate this binomial sum. K equal to I to j, n choose k, p power k, 1 minus p power n minus k, where p is the probability of success, 1 minus p is the probability of failure. The problem was not difficult. When you have small n, you plug in the values and you get the value. Okay, they didn't used to have calculators, so they used to calculate by hand. Right now you can do it by our software in your mobile calculator, anywhere you can do that. But when n is very large as compared to k, you have the problem, and that's a very fundamental problem, right? You will be getting a very large value of the summation. Within the few years, the following problem arises in sociological study. So there was a sociological study was going on in United Kingdom, in which people has to calculate for n equal to 11,429, I equal to 5745, and j equal to 6128. Right now, you try to understand, if you don't have any calculator, can you calculate this sum over k equal to 5745, 26128, n is your 11,429. Can you calculate this sum? Is it possible? Let me give you p value, p equal to half, say. That will be quite impossible. But these people, they didn't lose their mind, and they started doing that. So the original problem from which this particular expression came was the following. The problem that they have taken is to test the hypothesis that male and female births are equally likely against the actual birth in London over last 82 years. That is, the problem was taken back in 1710, and they have chosen the data from 1629 to 1710. They observed that during 1703, the ratio was around 0.50, and in 1661, the ratio was 0.53. So given that 11,429 is the average number of births in London over 82 years period of time, and 5745 was the minimum value of the number of births, and 6128 was the maximum value of the birth during that 82 years. So can you calculate, using the given information, the following summation? The summation will give us some idea about whether the hypothesis is true or wrong. To solve this hypothesis, they wanted to calculate the following probability. They choose p equal to half because you see it's 0.50 and 0.53. Approximately is half. So they, given p equal to half, they try to calculate the probability that x is lying between 5747 to 6128. Right now we are given with this sort of expression, summation of I equal to 5745 to 6128, and this big expression. How to solve this expression even without having a calculator? These people then came with the idea of recurrence relation that was incorporated in the combinatorial theory or combinatorics theory during that time. They came up with the solution of 0.292. But there were people who are not very happy with this solution. The greatest achievement or breakthrough that happened during this period of time is by de Moivre. He began the search for this approximation in 1721, and in 1733, he finally proved the following. He proved this particular combinatorial expression n choose n over 2 plus x into half power n is approximately equal to root over 2 over root over pi over n e power minus 2 into x square by n. From which he also came up with the idea of the following phenomena. Sum over n choose x half power n, where x is ranging between a plus n over 2 to a minus n over 2. He got the following expression, which are very close expression to the normal distribution. I know that because I'm presenting using the slide and it's mathematical, it might be looking a little challenging, but it's not at all. If you just try to calculate them by hand, it will be right now, it's very easy to understand. Eventually, using the second approximation, they came up with the sum over k equal to I to j, the particular binomial sum they were trying to calculate for large n. That's why we tell binomial sum converges to normal for large n. They tried to get a particular expression using normal distribution. And that's where they came up with the idea of normal distribution and standard normal distribution. So it all started with the gambling, and finally some mathematicians, they solved the problem that a gambler raised. So you can understand the importance of interdisciplinary research. During that time also people are doing interdisciplinary research. Being a statistician, it's very important to understand the impact of interdisciplinary research. During my stay at ISI, I have worked with physicists, I have worked with biologists, I have worked with computer scientists, I have worked with mathematicians, and even these days I'm working with industrial engineering people. I have taken a PhD student in economics. So you can understand, if you collaborate with people, you will be getting many problems to solve. Otherwise, in statistics, what problem you can get might be a very theoretical problem, maybe a mathematical statistics problem, rather than getting a data science problem. If you want to get really good data science problem, you should have good collaboration with some other people who are having the problems. As a statistician, you don't have your own problems. That's the beauty of the science, because we are just like sugar or salt. In every science, if we punch it with that sugar or salt in the food, it will be tasty based on the particular thing, whether you have to use sugar or salt. So that is the importance of that. And during that time, 17th century, the normal distribution got evolved. Back in 1809, Gauss, another very famous statistician, who is very famous for Gaussian distribution, of course. Normal distribution, you know it as a Gaussian distribution later on, because he proposed normal distribution as a error distribution. And you also know the name of Gauss if you studied something called ordinary least square estimation. So the method of ordinary least square estimation was proposed by Legendre and Gauss back in 1807 and 1809. So Gauss in 1809, he made the following assumption and deduced the normal distribution as an error distribution. And that is why whenever you write y equal to alpha plus beta xi plus ei, that is nothing but the simple linear regression model or linear model. You assume ei follows, ei is coming from IID normal 0, sigma square. So that's what Gauss did back in 1809, and we are using it in 2022 even. So small errors are more likely than the large errors. For real numbers, for any real numbers, epsilon, the likelihood of errors of magnitude epsilon and minus epsilon are equal. So based on this, he came up with the idea of error normality or error-based normal distribution. In the presence of several measurements of the same quantity, the most likely value of the quantity being measured is their average. So that's why he took x minus mu, and standard deviation he used because that was the most, because for normal distribution, taking the normality assumption, sigma square is nothing but will have the would be the nothing but the unbiased estimated of the population variance. So sigma hat will be the unbiased estimator of the population variance, which we measure by MS residual. So he came up with this idea, with this sort of idea during that time. And to read more about these particular derivations that I have shown and the error modeling approaches from where normal distribution can be derived, you may look into this particular very small 5-page magazine paper, which is nothing but the evolution of normal distribution, published in Mathematics magazine 2006. Just Google the evolution of normal distribution Mathematics magazine, the paper will be coming to you. It has an English version which is of 6 to 7 pages. Okay. Now, normal distribution, why it is so useful? Because it's the distribution which comes if you apply CLT to any other distributions. So if you have very small data, it might not be normal. If you have moderate, it might not be exactly looking like the bell-shaped curve. But if you have very large samples, it will be reaching to normal distribution. So that's why we have this Lindeberg-Levy central limit theorem. In case you are in BSc second or third year, you must have gone through this central limit theorem, which is nothing but if you take a sequence of random variable, which are IID, and having mu and variance sigma square, it may come from any distribution. Then we have root over of n into x bar minus mu over sigma follows standard normal distribution. So that's why normal distribution is more relevant in practical scenario. Whenever we get some data from other distributions, if we get many more data, if we keep on increasing n, it may boil down to normal distribution. Now, why I'm telling normality is a myth? Because many a times if you get the data, just like I think most of you are in Instagram and Twitter. If you are in Twitter, you can follow me. That's a publicity stunt anyway. So, but in Twitter, suppose, if we look at the follower of the people, let's take CR7, Cristiano Ronaldo or Lionel Messi and Virat Kohli, of course, Deepika Padukone and many others. They have the amount of followers to be in million. Of course, like myself and maybe some of you who doesn't have much follower and belong to my category, they will be having maybe 100 followers. If you see that data, it is not normal, right? If you look at the number of followers, very less number of people have very large number of followers, where very large amount of people have very less followers. Just like in case of income distribution in India, I can proudly say that Ambani, Tata, Birla, all these people, they have almost 80% of the currency of India with them rather than having rest of the people, right? So it's not at all normal, right? So what if the situation tells the data not to be symmetric? What if the data is a heavy tail data? It has a heavy tail behavior, just like this Pareto distribution and these other distributions. And another is, if the data is not unimodal, in normal you have only one mode, like you can get only at x equal to mu the modal value. What if it's a bimodal or trimodal or multimodal distribution? Can you really model it using normal distribution? Or what if the error distribution, just like you are assuming yi equal to alpha plus beta xi plus ei in simple linear regression model, what if the errors doesn't follow to be normal distribution? What if the error behave randomly? What if y even doesn't follow normal distribution if error doesn't follow normal distribution? What we are supposed to do? That's what you will be going to study during your master's degree maybe, or maybe advanced bachelor's degree. So I'll just give you those tools. What happens during these situations, how we solve this situation. I'll not be giving any solution for that. But if you want, I can share all the papers with you. And after your bachelor's background, I'm like almost guaranteeing you that you can read all those papers, because these papers are very, some of the papers are very old papers, as well as it's up to the mathematical standard of bachelor's level. So these are very interesting papers in that sense. Anyone can read. Suppose if the data doesn't follow normal distribution, can we design a skew normal distribution? The first thing is Yes, instead of using gamma, beta, Pareto, Poisson, not Poisson, Pareto, log normal, Rayleigh, anything, you can use Q normal distribution that was proposed by Azalini back in 1985, and it's a very big work that reached more than 2,500 citations over last 30 years. Then another work by one of my very like senior friend, as well as a very famous professor from Manchester. I think currently he's in Manchester. Rameshwar D. Gupta, he proposed something called power normal distribution. And power normal distribution idea comes from Lehman alternatives. So if you are going to study test of hypothesis, just look at the thing what is called Lehman alternatives. So Lehman is the person who wrote the book named as Test of Hypothesis, which is usually taught in ISI. So that book was written by Lehman, and he proposed an alternative hypothesis. Suppose F equal to G is a given distribution. We want to test that whether H1 is F equal to G power alpha. For any alpha greater than 0, that's called Lehman alternatives. Based on the idea, Gupta sir came up with the idea of power normal distribution. And very recently, Debashish Kundu sir, he's a very famous professor from India, IIT Kanpur, and he did his PhD under Professor Sierra. Okay, so even I learned about many things about normal distribution from Kundu sir when we met at ISI. So he published a paper in Shankha called Geometric Skew Normal Distribution. Here he used a very interesting idea that was proposed by Marshall and Olkin. Both of them are Stanford statisticians. They came up with a very interesting idea called Marshall-Olkin family of distribution. He used that idea to generate something called geometric skew normal distribution. So these things we will not be discussing, but these are the solutions. I'm just trying to give you the possible way out when the following situations happen, when there is no normality. And in case of regression, maybe during bachelor's, you'll be only studying linear regression models. But over the time, you'll be studying if the error distribution is not normal, we try for Box-Cox transformation. Again, the Box came. So Box will be coming in statistics on a daily basis. Okay. So Box is a very famous statistician, and he used to be very laughing statistician. He used to laugh a lot. He has a very nice face, very similar to, let's say, like Kapoor family people. So he looks like that, Kapoor family people, okay, in the Bollywood. So he's kind of the person who, if you look at his picture, you will laugh like that. He's a very funny person as well. He was, and he came up with the idea of Box-Cox transformation. When the error is not following normal, you transform the data, transform Y using Box-Cox transformation. That paper got published in Journal of Royal Statistical Society, Series B, and that's a very big journal in statistics, of course. Then another idea by Nelder and Wedderburn came in JRSS again. It's called generalized linear model, and there are various semi-parametric, non-parametric machine learning approaches which doesn't assume the normality of the data. All the machine learning approaches, most of the machine learning approaches I should share doesn't assume their own normality. So for learning all these approaches, you may look into the book called Elements of Statistical Learning and Introduction to Statistical Learning. Trust me, I'm right now teaching bachelor's students out here at Shobon, and I'm teaching these two books. So you can read these two books. You can understand that this is not a very math heavy one, or even if it is a math heavy one, you know this calculus, you know this algebra. I presume, okay? So this was all about the first section. I think I'm going a bit late. So just give me a reminder whenever you feel it's almost at the dead end. So the another topic I thought will be telling or giving you a headshot that correlation doesn't mean causation. This is very, very, very important thing to be understood. We'll try to understand what we really mean by that. Okay. So I think correlation has been introduced to you in the bachelor's first year. So if it was introduced to you, look for a paper called Association, Correlation and Causation, published by Altman et al. In Nature Methods. You'll be, if you just Google this particular name, you'll be getting it. And for the slide of my talk, it will be available tonight in LinkedIn or my web page. So you can download it from there and Google all these things, all these papers, if you want to study. Okay. And this particular paper, association, correlation, and causation, this gives a really nice example to distinguish between correlation and causation. And you'll love reading that paper. It's a very interesting paper. I take the abstract of the paper from the paper and write it at the top. Correlation implies association, or correlation may indicate any type of association for bivariate data set. Suppose we have one X, one Y, say I have all of your heights and all of your weights. I assume there is a relationship between them, which may not be true for many of us. Like my height is 5'5", but my weight is right now approaching towards 70, or not 70, I should say 65, because I don't walk a lot. So may not be true for me. Okay, so if you plot it in the regression line, it won't be suggesting that as the height increases, the weight increases. It won't be true. But it might be true for some of the data sets. So if you try to understand that association between these two variables, we try for scatter plot, we try for, say, Carl Pearson's correlation coefficient. If it is a categorical data, nominal data, we go for Spearman and correlation coefficient, Kendall's tau, and many other measures. So correlation essentially implies association, but not causation. Conversely, causation implies association, but not correlation. So it's the very funny example they have given here, which you may look into, and I'll be giving a funny example from my perspective. So this is a particular picture which suggests you when to understand there is high correlation, when not to understand very high or moderate correlation, when there is zero correlation between two variables. So we plot X and Y, two variables in the bivariate framework data in the XY plane, and this is what we can get. So correlation is clear, it's we all understood, but what is causality? So it's like during my first year of college, I used to think correlation implied causation. Then I took more statistics classes. Now I don't think that. Sounds like the class helped, right? So what is the cause and what is the effect here? So effect is that I used to understand correlation implies causation. Right now, all my wrong beliefs have been vanished. And what helped? What is the cause? That is the statistics classes. So causality is the central notion in science, decision making in daily life. Causal inference is nothing but causal modeling plus statistical inference. So this is a very new science which evolved in last 50 years. Or to say more, it got evolved back in 1000, I should say, with some of the very famous works I'll be discussing now. So what is causality? If we look at the definition of causality, a very famous book by David Hume, that is nothing but a treatise of human nature. He talked about a particular thing and defined something called cause and effect. He told, we remember to have seen that species of object we call flame, and to have felt that species of sensation we can heat. We likewise call to mind their constant conjunction in all the past instances. Without any further ceremony, we call the one as cause and another as effect. So this was a particular definition he gave from the psychological background and philosophical background, rather to say. And let me give you an example. Suppose a bird is carrying a baby. So he's carrying a baby. So does that mean that the stock really bring babies? Or the babies are born in some different way? So I'll connect this with the cause and effect thing. Okay. So causality is nothing but cause and effect science, where correlation essentially means there is an association, and many of the times we assume that correlation means causation, which may not be true in practice. That's what I'm trying to say. In statistics, we assume that's why that name is called fooled by statistics. Many of the things that is defined in such a way that you might be taking it for granted, don't take it for granted. That's what I'm trying to say. So this is the picture of the most famous statistician, I should say, Carl Pearson. So all the tests, all the methods you are studying, many of them are developed by Carl Pearson. He was a lab assistant of Sir Francis Galton, who created Galton's board, linear regression, and many other things. So he talked about this cause and effect during his 19th century. And then many a statistician, just like Terry Speed is a very famous biostatistician from Australia, and Muthen is a very famous statistician, they talked about this, that statisticians always try to avoid the causal reasoning. They always try to assume that correlation means causation, and you fitted a linear regression, multiple linear regression, machine learning model, all the model you created, you assume that the correlation means causation. But you might not be doing well for some particular examples. I'll take you to that example, to those examples now. Let's say in this particular example, you can see, does the stock really bring babies? Let's take this example. X influences or X causes Y, or vice versa. But does it hold really true? Or there are some another cause called Z, which is connected with maybe the reproduction system or something else which connects both of them. Like, it's nothing like a particular bird can create babies. It's like the reproduction system of animals or humans that actually creates both of them. So it's like there is another new factor which has emphasized on them rather than telling them as cause and effects. So that is what was defined by Hans back in his work called Common Cause Principle in 19th century. So this causal inference, which only talks about when to say it's a cause or effect relation and when not to say, that's what nothing but known as the causality theory. And this causality theory got lot of emphasis during the at the end of the 19th century and back in the 20th century. The famous people who worked on that is called Ronald Rubin. He's a very famous statistician. I hope he's from UK. Then Judea Pearl, one of the big shot in the field, and he won the Alan Turing Award for his works in causal statistics. So it's called the Nobel Prize in Computer Science. He got the Nobel Prize in Computer Science being a statistician who created causal statistics. So you have the chance still. So I'm just not discouraging you from getting a Nobel Prize in Computer Science, a Nobel Prize in Economics, or a Nobel Prize in Mathematics, which is like known as Field Medal. Then Donald Campbell, he also worked on that. David Philip, he is very famous for Philip's curve and Philip test. And then Granger's causality will be studying in your Bates and Granger model. Granger's causality will be studying in econometrics. So Granger also won Nobel Prize in Economics. He was a statistician, by the way. So being a statistics student, and being from ISI, I wanted to do my PhD in econometrics actually. Then I applied for PhD in IIM Bangalore in economics, and I didn't want to go abroad. So they asked me, why do you want to shift from statistics to economics? My answer was, I think one of the stupidest answer, but I told, like, in statistics we don't have any Nobel Prize, but in economics there is. So I might be looking for that. So though I was very serious about that, really. And right now, after doing PhD, I feel like I was a stupid to give this such a type of answer. So, but yeah, so being a statistician, Granger won Nobel Prize in economics for his very famous work on modified version of ARIMA model, ARFIMA model, related work on VAMA model, Granger's causality test, and many other, which is very strong application in economics, social science, and many other disciplines. So these are the persons about whom you will be knowing slowly during your master's degree. Right now, I'll connect this causality with machine learning. So I think most of you came here with the idea that you will be learning a little bit of machine learning, but I'm disappointing you. But right now, I'll go a little bit about machine learning. So knowingly or unknowingly, regularly we use machine learning. We may not know that. Maybe when we set alarm, we tell, okay, Google, set an alarm at say 9 o'clock. or 10 o'clock because I had a talk from 11 o'clock. If I was a student, I used to be okay at 10 o'clock or 10:30 to attend this particular seminar. I'm a late riser. So, but you shouldn't be, but anyway, so that's how when we talk with Google, we use something called natural language processing. We talk in our own language. The Google Translator, it uses a particular language model or GPT model or transformer model, which transforms my language to the language understandable by the machine. And it uses nothing but a strong statistical neural network model. So that's the beauty of learning statistics and machine learning. So then we book our cab, we go to our job place or colleges. So during the thing, we uses Google Maps. Do you think there were a lot of drones traveling outside your home? I believe no. So all the images that is given in Google Maps, many of the images are only taken by satellite. Satellite is projected and at the top of the earth, and it is getting all the images, and it's very difficult job for a machine learning or image processing personnel to really correctify those images and create a very strong and nice image of that. Just like even if you are using Samsung S22 or Apple, the latest version, then also I think you cannot take a very clean picture from one end of the field to another end of the field, right? Just like a satellite is taking image from the at the top of the earth and creating these beautiful images that we are using in Google Maps. It's fascinating, right? Of course, the science of machine learning is definitely fascinating. That's right. And machine learning uses all the statistical tools. That's another thing. So if you unbox machine learning, it's more about mathematics and statistics and computer science tools. Then we do whatever we do during the search engine. Whenever we search, say for a pen, or we find a mobile, they will be showcasing us some screen protector or something else in Amazon or Flipkart, whatever you use. Whenever you order, it also does the very same thing for understanding what the next item you are likely to order. So machine learning has got its application in our day-to-day life. But right now, we want to apply machine learning in healthcare, law, and the automated cars or autonomous driving cars, fintech, for taking the very risky decision. And these risk-sensitive decisions is something which is stopping machine learning. And what is stopping machine learning to perform the best? One of the things is nothing but the caution. So most machine learning models are assumed as black box model. So you want more explainability machine learning. So that is one of the key area of research. Whenever I do some machine learning, I create some machine learning model, I try to create it in such a way that it should be explainable and interpretable. So that is one of the things in which people are currently looking for. And most ML-based method, they really work well on the training data or on which data you build a model. If you use the model for another data, it doesn't work. Suppose that I create a height distribution for the people in India. And then I want to use this height distribution in France. And trust me, all my colleagues have almost 1 feet higher height than me. Like, I don't know how, but all the Europeans, they seem to be 6'5". So it's like I have to look at their face like this. If be it in boy or girl, doesn't matter, irrespective of the gender. So it's a very bad thing for me being in the teachers table with people who are having at least 1 feet higher height than myself sometimes. But that's what happens if you build a model for the people of India with their height and you map it to US or Europe. That's when all the machine learning and statistical models fails because of the IID hypothesis and the assumptions that they make. Because the training and testing data, they changes a lot. There is a data shift. Along with that, in machine learning, another problem that occurs is this particular problem of stability. Suppose these are the very cute pictures, as you can see. If we train a model with the pictures of this pet at the left, say Sky to be the name of this particular dog, and we take all their pictures, and we try to understand based on these 5 pictures whether the right side pictures a dog or not. Maybe the last picture it will not understand as a dog. So that's what the problem of ML models. That is nothing but stability. And from here, the adversarial attack problems have been introduced in machine learning, which still now people are trying to solve. If we can solve that in a great manner, then we'll be having autonomous driving car everywhere in the world. Then another problem is, like, if we create a data training data from some particular city hospital, if we apply it for university hospital, it won't work. Or maybe another issue that machine learning models or statistical models have, because of the wrong understanding of correlation and causation, or the interconnection is sometimes not established. Suppose if you are working in a company, and just like me, many of the people are losing hair, and they are shaving their head. Okay. So, and accordingly, you have observed how many people shave their head in last 12 months. And you observe the sales figure of the company, and you can see both are showing a very positive correlation. So the CEO of the company came and told, oh, this is nice. So can we have razor and just make everyone bald? Would you support that? I think you guys shouldn't. But so that is one of the things that happens when you take correlation as causation. It might be sometimes not implying that. Or another great example was given in a particular paper, that is, people who drowned after falling out of fishing boat and the marriage rate in Kentucky. If we look at the data, we may see that they looks very similar, and there is a very strong correlation between them. Is it a cause and effect relationship? It shouldn't be, right? In case you are planning to get married within next 2, 3, or 4 years, then if you look at this data, you will be like, no, I'm not going to do that. So it is something very astonishing, but it's not true, because these two phenomena occur differently. That cannot be cause and effect. So correlation is very unstable. That's what the problem is. And most of the statistical and machine learning model, they assumed took correlation very seriously, and they took it as a causation. And that's why when we try to understand various different typical images of the different pets, so we may fail sometimes to identify that it's a dog of the pet or not. So it's not fault of correlation, but the way we use it. So correlation, how to distinguish between them? So causation is nothing but causal mechanism and stable and explainable. Just like in summer, the sales of ice creams get increased. And another case could be confounding. So whenever you are going to study design of experiments, you will be studying more about confounding. So confounding, there is maybe something called income actually helps us to buy some financial product offer, and we may accept some of the things, some of the policies maybe. So then it's nothing but financial product offer and acceptance, they have a correlation. It's a causation. It's another particular thing, income, which has effect on that. And that's what confounding means. In design of experiment, you'll be learning more about that. And under that, there comes something called spurious correlation, just like the correlation with the sales and the head shaving people. I give the example for a company. And also causation occurs due to sample selection bias. So this is something you should be looking for. So maybe you have to choose some more images of grass and dogs to identify between which are dogs, which are grass. So that's what I'm trying to differentiate between correlation and causation. So T causes Y if and only if changing in T leads to a changing in Y, while everything else should be constant. That's what I mean by causation. But in correlation, it doesn't happen. Not everything else should be taken as constant. That's why this particular science has got much attention. And in the world, let me tell you, in India, you'll be finding hardly 2-3 people who works in causality. So in case if you are planning to do a master's or PhD, if you work in causal science, it has got its application in every single field. And one of such example I have presented here It has application in economics, medicine, philosophy, computer science, epidemiology, everywhere. And if you can really come up with some nice understanding how to differentiate between them, instead of using Range's causality or the idea that Julia Paul and other people proposed, you will be a big person in the field. And that's a very new field in terms of saying, because I could see very less Indian guy there working on this particular field, as well as there are very few like other people in the world who really works on that field. So it's a very interesting field to work on. So right now I'll end the session of correlation implies doesn't imply causation with this particular example. I don't think this example is a very appropriate one, but take it lightly. Okay. So suppose you found one of your friend who was sleeping with shoes. Suppose you stay in a hostel and a particular some of your friend came and he or she slept with shoes, and the next day he is going to have headache. Are you going to tell that sleeping with shoes causes headache, or headache is caused by sleeping with shoes? May not be. There might be another particular variable. Might be the case she was ill or he was ill, or maybe he or she was drunk. That's why that's the particular Z variable which actually let these two events occur together. So that's when we don't see causal association between sleeping with shoes and getting headache, rather than it is caused by either drinking or maybe being ill. So that's a very, very interesting example where correlation means causation, or when correlation doesn't mean causation. So this is a very interesting example drawn from Brady Neal's webpage. He is a statistician who is completing his PhD in Montreal, I guess. So he has a lot of really interesting lecture notes on causal statistics. In case you are completing your bachelor's, you have short of 1 month time to spend, have fun. You might be doing that course online. It's available in YouTube. Just check Brady Neal causal inference course. So maybe the potential, I tried to explain here what do we mean by correlation, what do we mean by causation, how they are different, how an extra confounding effect or a third variable can make this ambiguity to incur. Okay. So what are the solutions for this? So right now we have the following solutions given by various statisticians and epidemiologists and machine learning people to work using graphs, using Bayesian graph model, Bayesian network model, structural equation based modeling things in econometrics, and counterfactual words. So these are the three different languages for causality which are usually taught in causal inference class. There is if you are someone who loves to read book, if you love to read some motivational book or some story books, this is a story book that I'll recommend to you. The Book of Why, written very recently in 2019 by Julia Paul and Dana, who is a reporter who made Julia Paul, and they wrote the book together. That's another funny story. But the Book of Why. So it's published by Penguin, so you can understand that's not a very technical book. So another book I should recommend you, from which the title of the talk came, that is nothing but Fooled by Randomness. That's a very interesting book. It's also a story book which talks about, and another book on black swans, why some of the random events are very difficult to forecast, difficult to predict, difficult to use statistics and machine learning out there. So it will give you a very interesting idea about financial market. The black swans and the fooled by randomness will give you a lot of examples how we get fooled by the randomness in nature. The last thing, I'll just take another 5 to 10 minutes, maybe I'll finish. I always exceed the time, that's the bad thing. So all models are wrong, but some are useful. This was told by George Box. So for this, I'll give you an example from forecasting. So forecasting is nothing but, just like right now, who will be winning the Oscar next year? So right now, I think Oscar video of Smith hitting his friend got or and a comedian, it got very viral. But if you want to predict who will be winning the Oscar or who will be winning the World Cup, football World Cup is coming in Qatar. I really want to go and see. But who will be winning the election in India? All these questions, or what will be the exchange rate, because I stay outside India, exchange rate is very vital for me. Whenever the exchange rate, whenever Indian economy is down, it's like, based on my personal perspective, I gain. Okay, so but which shouldn't be the case, but financially I gain that time because the exchange rate is very high that time. So if we can get some idea and forecast them, or if we can estimate this sequence of observations, how they are going to behave in real time for the next few days, we are going to get some idea. And if you can predict stock market, if you can predict the temperature for tomorrow, just like in Google, they use machine learning models to, not machine learning, they use actually a spatio-temporal model based on a spatial deep learning model that they use for forecasting the temperature. Just like that is why, if you see the temperature of, say, Wednesday, today, so in the next Wednesday temperature, if you look at today, and if you look at tomorrow, it will be changing, because once the new data came, they keep on changing their predictions. So if you are interested about this area has also got a lot of fascinations in, from the weather, climate forecasting, electricity consumption forecasting, and during the COVID, how to forecast COVID, where many of the people got wrong. In during that time, I was at ISI and I was at home as well for a couple of months, and during the lockdown, and I could see many people coming with a simple SIR model, and during the television interview, they are telling, okay, this will vanish in next 2-3 months. So I was not very satisfied, because SIR model is a deterministic model. It has many assumptions which nowhere at all true for India, at least, and anywhere in the world, it seems, because there is a change in the population, exchange in the population was going on. So epidemiological forecasting is another sort of thing you might be interested. And of course, economic and financial forecasting, in which I also work. Right now, I'm working more on to CPI inflation forecasting with people from IIM and BITS and some people from RBI. So time series forecasting is one of the particular area where we try to forecast or extrapolate based on the given signals, and we try to reduce the noise or uncertainty minimization of the, or risk minimization or uncertainty assertion is the one of the tasks in forecasting. Let's take this particular example from the Australia. So this is the tourism, number of tourist visitors in Australia. If we have this particular data from 2012 to 2020, nobody could estimate that in 2000 suddenly COVID happened and everything got ruined. So if you even if you are a really good forecaster, you might be forecasting those blue lines. You never had the idea that COVID will come. So mathematical and statistical models, they always assume that the other things are really getting constant. There is no natural phenomena, some natural calamity that is going to happen in between, which will erase everything, whatever I have done, and it will make a new trend. So that's where forecasts sometimes get wrong. That's why I'm trying to tell, all models are wrong, but few are useful. Still, we need these models. What if COVID didn't happen? Then might be our forecast would have been really correct. So that's what known as black swans. Black swan, it's a very famous book written by Taleb. So he talks about Nassim Taleb, he talks about this particular idea. He's a New York's university statistician. He talks about the idea of why it is difficult to model the black swans, just like this COVID all on a sudden happens. Just like what is easier to forecast, what is difficult to forecast. Maybe sunrise, what will be the sunrise time next day? So what will be the maximum temperature tomorrow? Maybe what will be the daily electricity consumption? But predicting the Google stock price or exchange rate is very difficult. Unless you have really controlled, you have really some control variable on which you have great idea. So what makes some things easiest to forecast and difficult to forecast? Something like if we know the factors that are contributing to that. Just like stock price depend on many things. It depends on inflation, deflation, it depends on the exchange rate, it depends on the commodity price, it depends on the import, export, many other things, right? So it depends on the even the natural calamity that is happening, the situation. So we cannot really forecast, say, CPI index without knowing the geopolitical structure of the country. Or just only knowing that some macroeconomic variable is not sufficient. If we have those sort of data sets, it's very easy to forecast. It's at least triable to forecast. We need a lot of data. Unless we have data, forecast might be wrong. Just like what happened during pandemic. People tried to use the epidemiological model, and many of the times they were wrong. But still, it gives some idea about how the COVID will behave. Maybe next time, if we get some disease very similar to COVID, we'll have the past idea. Future is somewhat similar to the past, because in COVID, the second wave was very dissimilar to the first wave, right? So if that is the case, statistical and machine learning model may fail. Or your forecast shouldn't be affecting the variable you are trying to forecast. Suppose you predict the stock price for next 7 days, and all on a sudden, Warren Buffett tells something bad about that particular stock. Or Jhunjhunwala, he talks about something from Indian market, stock market. Stock price fall down, and you will be like, you'll be threatened by the people whom you give the advice to put your money on Paytm or something like that. So you will be in like great trouble, right? Because some of the people, big bulls are there. If they make some comments, that changes the forecast. That's why it's very difficult to forecast the stock price actually. And when we should have, when there is insufficient data, when there is the models give implausible forecast, we need to stop. I'll not go through this slide because it talks about various forecasting models that are derived in the future. To understand what are the forecasting models are there. If you have studied time series forecasting in your graduation till now, or maybe you read the book by Chatfield, time series forecasting, or some other book, Gun Gupta, Das Gupta, time series chapter, or Gupta Kapoor book, you can have a look at this paper called Nowcasting COVID-19 Confirmed Cases, Trend Foundation, and Challenges by myself and my co-authors. It is publicly available. If you do not get the copy, just email me, I'll send you the copy. It's a tutorial note written for anyone interested in forecasting. So it's just to motivate you and to give you an interest, how do we really forecast, to give you an idea. So this is not very technical. You will be getting very brief idea or broad of how forecasting actually works. Now I'll come to the caution thing. So forecasts can go very, very wrong. Niels Bohr, the Nobel laureate in physics, he told prediction is very difficult, especially if it's about the future. Some of the forecasts that went terribly wrong was IBM chairman in 1943, they told, I think there is a world market of maybe 5 computers. Then the chairman was replaced by another chairman. That's what happened. If you make a wrong forecast, might be replaced in from your organization. So be cautious. And the DC Computer is was a very popular company, American company, who used to produce computers, manufacture computers. Their president in 1977 told there is no reason anyone would want a computer in their home. You know what happened in 1980? IBM came with the first home computer, and the company DC Computers right now no more exists. It got bankrupted in 1980s. So if you make the following forecast, you might be replaced. Another person who got replaced is Donald Trump. He told in February 2020, we are going to be opening relatively soon, the virus will go away. So don't make wrong forecast. Another very interesting forecast that CEO of Microsoft told, there is no chance iPhone will be having a significant market share. In 2007 and right now, I think in I have to stay in 2 places. One is in United Arab Emirates, that is Dubai and Abu Dhabi. Another is in France, Paris, France, of the Sorbonne campus. We have these 2 campuses of Sorbonne University. I can see these two campuses, most of the people uses Apple. So how terribly the CEO of Microsoft took those claims, and it was a mess, of course. So I'll end up here. So I think you try to understand these three phenomena. One is normality is assumed for better understanding of the phenomena, but sometimes it may go wrong. We many a times assume that correlation means causation, which may not be true sometimes. We forecast many a event, we do a lot of prediction using statistical and machine learning model. It may sometimes go wrong, but if you do it carefully and if you know when to stop and when to speak, then that will be really good thing. And talking about speaking, I have talked enough, I think more than 1 hour. So I'll stop my presentation now. And thank you everyone. Please feel free to ask any of the questions that you have. I would love to interact with all of you. That's why I said yes for this workshop to your madam. So that's the one of the reason I want to interact with all of you. Please feel free to ask whatever questions you have.
Dear audience, if you have any question, so please ask.
I think there could be some of you who will be thinking like if we ask the question, it may look stupid. So I think it won't be more stupid than what I told during my IIM Bangalore interview for joining PhD in economics. So feel free to ask. There is nothing called stupid.
I think there is no any question, sir. Thank you, sir,
Okay.
for coming and making the event is more successful. I'm giving a thank you from the bottom of my heart on behalf of Department of Statistics, Shaheed Rajguru College, for taking time from your busy schedule to be the guest speaker in this event. Your presence and wise words helps magnify our cause in the best possible way. This event is being a huge success, as showing the presence of audience approximate 70 plus. So, all thanks to your enlightening words of knowledge that inspire so many audience out there. Uh, Soon, we wish look forward to our next interaction in the future. Thank you, sir.
Okay. Thank you everyone. Yeah. Of course, thank you for inviting me. And I request all the students, if you feel very shy to ask a question publicly, you may definitely email me. My email address is always available there. You can email me your question. I'll be happy to answer. I always reply to each and every email.
या सर एक्चुअली मैं यही बोलना चाहती हूँ कि आपने एक ओनली वन मैसेज पर इतना अच्छा मतलब हम लोगों को एकदम से आप यहाँ पर आए तो थैंक यू सर इतना प्रॉम्प्ट
And for this presentation, I didn't sleep too much last night because I have to prepare the presentation. I was not at all prepared because I have a lot of teaching stuffs out here right now going on at shop. So anyway, but I think it was helpful for the students, hopefully.
Hope our all audience enjoy this event, and thank you audience to make the event successful. And now in the last we are going to take a group picture, so please unmute your sorry uh, please show your videos, and Vanna, please take a picture, beta.
Yeah, ma'am.
Dear audience, please show your videos. Actually, it's taking some time because of network.
Yeah, I think since they're at home, they might not be in a good place to turn on their video. So that's why they are taking some time.
Right? Vanna, please click a picture, beta.
Yes, ma'am, I have taken the picture.
Not one, two, three clicks you can take. Done?
Yes, ma'am, done.
Okay, all good. Okay, thank you very much. Yeah, yeah. See you. Yeah.